All right, let's do Taylor series and Maclaurin series. This is sort of the meat of this unit, what we've been working up to. We're going to start off with a little reminder from Calc 1, which is linear approximation of a function. So the linear approximation uses the tangent line to estimate a y value of a function. The linear approximation is actually the equation of that tangent line. So this is a reminder of what the equation of the tangent line is. In Calc 1, you might have had that written as y equals y1 plus m times x minus x1. You might have had it written that way. It means the exact same thing, except for instead of an x1, I'm using the letter a. Even in algebra, you might have had that written as y minus y1 equals m times x minus x1. Also exactly the same. I'm just choosing to get y by itself, so I'm bringing the y to the other side of the equal sign. Lots of different ways to write it. The way we're going to use is y equals f of a plus f prime of a, which is the slope of that tangent line, times x minus a. This is a linear approximation. It's linear, it's of degree 1, so we call it P1, just for the vocabulary, just so we're using the right vocabulary. Let me remind you what the intention of the linear approximation was. If I have some arbitrary function, we'll call it f of x. And I find some point, we'll call it a. Maybe it's 0, maybe it's 1, I don't know. That point isn't on the x-axis. And then I find the equation of the tangent line at that point. You should be able to notice that if you zoom in real close, the function itself is pretty close to that tangent line. It's not perfect, but it's pretty close. And if I were to get even closer to that x value of a, the tangent line is pretty close to the function. So that's something to keep in mind. The main thing to notice is that was just a way to estimate the y value. That's really what that was. So that was the linear approximation. What I want to do is I want to think about maybe a quadratic approximation. What if I think of a parabola? Wouldn't that be a better estimate of that function? And let's do that. Let's do the quadratic approximation for a function. What I want to get that better approximation, and I'm going to write down what it is that I want. What I really want is not only for their slopes to match their first derivative, which was the linear approximation. So I want that P1 of a prime to be the same as the actual function's derivative as well. I wanted their slopes to be the same. That was linear approximation. But I also now want, if I want a quadratic or a parabola to estimate this better, I want I'm going to call it what it is, the concavity. The concavity to match. Think of Calc 1 when we were finding increasing and decreasing. We used the first derivative when we were finding concave up and concave down. We were using the second derivative to make the quadratic in the same shape. So for this example that you see on the screen right here, I want that quadratic to be an upside up parabola. I do not want it to be an upside down parabola because in this particular case, the upside down parabola is not a good estimate of the function in question. So that means what I really want is I want the second derivative, or their concavity, to also be the same. So I'm going to come up with a new approximation that we're going to call it a quadratic approximation. I want the linear approximation to still hold true because that was still a good starting point. I'm just going to add on the quadratic term. The question now is, what should this coefficient be to make sure that the concavity matches? I want to make a note here to the side. The A is the center. Okay, the A is the center. It's just a number. It's a number. It's a constant. It might be 0. It might be 12. It's not really the point. Okay, so let's try to do that. Let's figure out what that C2, that second coefficient in my quadratic approximation should be. So I'm going to write down what we said our quadratic approximation was, which is P2 of x equals f of a plus f prime of a times x minus a plus something times x minus a squared. I'm going to take the first derivative. We're going to take the first derivative of that function. A is a number. So the derivative of f of a is 0. And then again, excuse me, f of a is a number. So f prime of a is a number. It's a constant, in this case, multiple. So it stays. So f prime of a. And then the derivative of x is 1. The derivative of a is 0. We don't need to write those, but they are there. Plus, oh, so sorry about that. Sorry about that. There we go. That's better. Plus, and then I'm going to take the derivative of this guy, bring the 2 down. then I would get 2 times C2 x minus a to the 1. And then it's time to try to find the second derivative. So that was the first derivative. I'm going to now find the second derivative to see what happens. The derivative of 0 is 0. The derivative now of just a number, that slope there, is just a 0, plus 2c2 are now constant multiples, so they will stay. And then the derivative of x is 1. The derivative of a is 0. So I ended up with here my second derivative, p2 double prime of that quadratic approximation is 2c2. But I want that to equal the concavity of my original function at that point so that I could have a good quadratic approximation. So I set those two equal to each other, and I have identified that that second coefficient, my C2, should be f double prime of a over 2. So now let's write that down. So now I know that a good quadratic approximation is f of a plus f prime of a times x minus a plus f double prime of a over 2 times x minus a squared. This is sort of the key conclusion. Now I could also move on then and find the cubic approximation, and it would be very similar, but I have to take 3 derivatives. I would bring the 2 down, but then I would also have to bring a 3 down, so I would end up with a 3 times 2. This would end up with a 6 on the bottom for the next term, and then you would end up with a 4 factorial and a 5 factorial, and that repetition would continue. Okay, so all that to say, we now have a definition for Taylor polynomials. Taylor was the name of the mathematician. These are called Taylor polynomials because they are polynomials that are going to estimate a function. Now, as soon as we make them infinite, they would then be called Taylor series. It's the only difference between them. They're still polynomials, okay? They're just one's infinite, one's not. So a Taylor polynomial, if f is a function with, let's say, the first k derivatives, maybe I didn't want to stop at a quadratic. Maybe I didn't want to stop at a cubic. Maybe I want to move on to the power of 9. That would be my k. To find a, the kth order Taylor polynomial for f with its center at a, denoted as p sub k, has the property that it matches f in value, slope, and all derivatives. F of a is the same as p of a. F prime of a is the same as p prime of a. F double prime of a is the same as p double prime of a. Up to the kth derivative. And then the kth order Taylor polynomial is p sub k of x equals f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared plus f triple prime of a over 3 factorial times x minus a cubed plus f to the fourth derivative at a divided by 4 factorial times x minus a to the 4, etc., etc., etc. And then, of course, infinite if it were a series. Okay, the only difference between a Taylor series and a Maclaurin series is the center. Okay, Maclaurin series is just a special case of the Taylor series when it's centered at 0. They're the same, just one of them is only centered at 0. Taylor series could be centered anywhere. So don't overcomplicate those, they're the same. Okay, so let's find some Taylor polynomials for sine of x. Now, before I find those Taylor polynomials, I actually want to get a nice little visual here so you can see what it is that we're doing here. Here is the sine function, and I'm going to center this at 0, and I'm going to first find the equation of the tangent line. That's that straight line that you see right there. Then I would try to find a quadratic to make it a better approximation, or a cubic function. Let's move on and try to find a cubic function. Here's a nice cubic function that looks closer to the sine function. And then if I do another higher order, and I keep going and going and going and going and going, you see how this just got better and better. And it almost looked like that infinite polynomial lined up exactly with the sine function. And it really did. Now, only partly because I didn't actually write out infinitely many terms of the polynomial. But if I zoom in, that is truly the best approximation I can come up with. Okay, now let's practice with some examples. So find the 7th order Taylor polynomial, we'll call it p sub 7, centered at x equals 0, which makes it a Maclaurin polynomial, but we can still call it Taylor, that's fine, for this function f of x equals sine of x. Then find the Taylor series for this entire function centered at 0, which would be the Maclaurin series. Here's how we do it. You know that I need the 7th order Taylor polynomial, which means you are going to need 7 derivatives. So I highly recommend that you start off with those 7 derivatives from the beginning. So I need f of x, and then f prime, and then f double prime, and then f triple prime, and then I'm going to need the 4th derivative, and then I'm going to need the 5th derivative, the 6th, that was a Roman numeral 6, there we go, and the 7th derivative. Let's find all of them first. I'm going to kind of squeeze that down to be all on one screen. There we go. We can find these derivatives. I know we can. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is sine. And then we can continue on. You can do this obviously all day long, and I certainly don't intend for you to do it all day long, only up to the 7th term. Okay, I found all the derivatives. I find all of them first. The next thing I need to do is find those specific derivatives at the center, because you have a center for that Taylor series. In this case, it said, if I can remember correctly, it says, where is it? There it is. It says centered at x equals 0. So I need to make sure I'm doing all of those values at the x value of 0. That means I should be plugging in x equals 0 everywhere for all of those derivatives. Sine of 0 is 0. Cosine of 0 is 1. Sine of 0 is 0. Negative cosine of 0 is negative 1, and so on. Okay, and then I'm going to write out what the Taylor polynomial is. So I'm going to run out of space, so it's going to take up some space over here. We got this. P sub 7 of x is f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared plus f triple prime of a over 3 factorial times x minus a cubed, there we go, plus the 4th derivative at a over 4 factorial times x minus a to the 4th plus all the way until I get to the 7th derivative at a over 7 factorial times x minus a to the 7th. That's the formula. That's the 7th order Taylor polynomial. So in this case, f of a plus f prime of a times x minus a. Now my center is 0, so that's going to become an x minus 0, plus f double prime of a over 2 factorial times x minus 0 squared, plus the 3rd derivative, which was negative 1 over 3 factorial times x minus a cubed. I'm going to stop writing the minus 0, because we know what the minus 0 is going to turn into. So I'm going to simplify this. I'm not done, but I'm just going to erase what I've got and try it again with some simplification. That was a 1 times x minus 0 plus 0 over 2 factorial times x squared, which we don't need to write, of course, minus 1 over 3 factorial times x cubed, plus 0 over 4 factorial times x to the 4th, because the 4th derivative was 0, by the way. And then I continue on, I'm almost there, plus the 5th derivative was 1 over 5 factorial x to the 5, plus 0, because the 6th derivative was 0, and then minus 1 over 7 factorial x to the 7th. Okay, let's rewrite that. So P sub 7 was x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5 minus 1 over 7 factorial x to the 7th. Ta-da. So I found the 7th order Taylor polynomial for sine of x centered at 0. There was a part B to that question. Part B says, find the Taylor series. Now it says find the Taylor series for sine of x. So that Taylor series really just means, do you recognize a pattern in the work that you were just doing? If you were to continue that on forever, could you write down a power series? And we can notice that pattern. We notice, look at that Taylor polynomial. It's as obvious as it seems. It's definitely alternating. Positive, negative, positive, negative, positive, negative. We know that. It also has a factorial on the bottom. It also has x to the power of something on the top, and every exponent is odd. And remember that 2n plus 1 is how we identify the odd powers. You should always double check. Plug in n equals 0. Did I get a power of 1? Yes. Plug in n equals 1. Did I get a power of 3? Good. Plug in n equals 2. Did I get a power of 5? We're good. And then you should notice the pattern was the factorial on the bottom was the exact same as that exponent. So this is the Taylor series for sine of x centered at 0. So I could go on. I could go all the way to like 100, let's say, write out that 100th order Taylor polynomial. If I want to know what sine of 2 is, like 2, just 2, sine of 2 is not on your unit circle. You would plug 2 into here. That's how your calculator knows that decimal. That's how it does it, right? I don't know what your calculator is coded to go up to, probably past 7, probably the first 20. I don't even know. I really don't. But to be honest, this is actually what they're doing. That's what your calculator is doing. It doesn't know what sine of 2 is, but it does know the Taylor series. All right, let's do the same thing, but now we have an ln function. So now we've got everything that we need. The process is exactly the same. Now we just continue it on. Now I want the 4th order. So I'm going to need 4 derivatives. So I start off with the derivatives. My function is ln of x. Let's do 4 derivatives. The first derivative is 1 over x, which I like to think of as x to the negative 1, because then its second derivative is negative x to the negative 2. The third derivative is positive 2x to the negative 3. And the 4th derivative is negative 6x to the negative 4. It only asked for the 4th, so we can just kind of go up to the 4th, and that's it. And then you got to remember where it's centered at. In this case, it's at the x value of 1. Whether you call it x equals or a equals, that doesn't matter. It's the center. The word center is the most important. So whether you call it x or a doesn't matter, but the word center does matter. So ln of 1, which is 0, 1 over 1, negative 1 to the negative 2. I just plugged in 1 everywhere. And then we have our 4th order Taylor polynomial, which is f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared plus f triple prime of a over 3 factorial times x minus a cubed plus the 4th derivative at a over 4 factorial times x minus a to the 4th. I just wrote it down first, and then I'll plug in my numbers. So f of a plus f prime of a times x minus a. Remember here, a is your center, and here a is 1. Plus my second derivative over 2 factorial times x minus 1 squared. Plus my third derivative over 3 factorial times x minus 1 cubed. Plus my 4th derivative over 4 factorial times x minus 1 to the 4th. So here is your P4. I'm going to simplify it, but that really is all that the question asked for. I'll simplify it. We might as well. So P4 is 1 x minus 1 minus 1 half x minus 1 squared plus, I'm just going to use my calculator, 2 divided by 3 factorial is 1/3 times x minus 1 cubed. And same thing, 4 factorial is 4 times 3 times 2 times 1. And you know what 6 is? You can simplify those easily. I ended up with negative 1/4 x minus 1 to the 4th. Ta-da! So there was your 4th order Taylor polynomial, definitely Taylor because it's not centered at 0. This is centered at 1. Taylor polynomial for the function ln of x. Ta-da! So if I wanted to know, let's say, what ln of 1.3 is, to figure out what ln of 1.3 is, plug 1.3 into here. That's a pretty good estimate. That's how your calculator's doing it. It's probably doing more than just 4. It seriously probably is. Maybe 20, maybe 100. I don't know how the calculator's programmed it. Definitely more than 4, but I do know that's how it's calculating it. We don't actually know what ln of 4 is or what ln of 1.3 is. We only know this Taylor series representation. All right. Okay, so same thing. Now we're going to do an e to the x, though. Very similar ideas. I'm just going to get a nice practice for this one. This one's maybe a little bit easier, but we can do it. So f of x is e to the negative x. It's only asking for a third order Taylor polynomial. So I only need 3 derivatives, and I will do that here. And then each of those derivatives, I'm going to plug in my center. And here the center is at 1. Everyone's a little bit different. Make sure you just read the question. So e to the negative 1, negative e to the negative 1, e to the negative 1, and negative e to the negative 1. And then now I bet I can skip writing the formula because I have it in my head. So the third order Taylor polynomial is f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared plus f triple prime of a over 3 factorial times x minus a cubed. Ta-da. Remember, it's after you plugged in your a. Those are the coefficients, not the variables. You don't have extra variables in the coefficients. The only variables that you have are the x's. Ta-da. Cool. Okay, let's do another one. So same kind of idea, maybe just slightly better. More practice, really just more of the same thing now. Find the third order Taylor polynomial for f of x equals e to the x, centered at 0. And then I'm going to use that third order Taylor polynomial to approximate the value of e to the power of 0.1. And then I want to find the Taylor series, so that would be infinite, for this function centered at 0. Let's start at the beginning. First thing it asks for is a third order Taylor polynomial. So I'm going to need 3 derivatives. So I write out the original. You always need the original as well as the derivatives. Always need all of them. So f of x is e to the x. F prime is e to the x. F double prime is e to the x. F triple prime, you can imagine how simple this one would be, which is great. All right, and then I'm going to plug in the values. Where are we at here? Centered at, my center is 0 here. So I plugged in 0, e to the 0 is 1. E to the 0 is 1, e to the 0 is 1, e to the 0 is 1. Let's write down the Taylor polynomial one more time. Third order Taylor polynomial is going to be f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared plus f triple prime of a over 3 factorial times x minus a cubed. The more you write it down, the easier it's going to be for you to remember it. So if you write that in your own handwriting, then we can just plug in what we have. F of a was 1, plus f prime of a was 1, times x minus a, but my a is my center, so all of those a's are 0, so I'm not going to write the minus 0 anymore, plus f double prime of a over 2 factorial times x minus a squared, plus f triple prime of a over 3 factorial times x minus a cubed, which I like to simplify, although you don't need to. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial. That is my third order Taylor polynomial for e to the x centered at 0. So that was specifically for e to the x centered at 0. There was a little bit more that it asked. It asked to use that third order Taylor polynomial to approximate e to the 0.1. So let's do that. So e to the 0.1, this notation matters, is approximately equal to the third order Taylor polynomial at 0.1. So now I just plug 0.1 into the polynomial that I just found. Feel free to turn everything into fractions if you would prefer, but of course you're allowed a calculator, so I'm totally fine if you just type that in. I got, oh, sorry. That's not what I got. Let me try that again. I got 1.1051667. If you're willing to trust. I did type it into my calculator. Of course, there's a million ways you can go about doing that, but okay. All right, cool. So that's the approximation. Let's talk about an error though. I know the question didn't ask. I am kind of curious of what the absolute error is. So into my calculator, I'm going to type in exactly this, which is e to the power of 0.1 minus 1.105167, because I want to know e to the 0.1, what my calculator says e to the power of 0.1 is. My calculator, I'm going to write it down, says it's 1.10517. Hey, my approximation was pretty close. That just tells me that my calculator is still using a Taylor series, but it's probably not stopping at 3. It's probably going up to like maybe 20, maybe 100. I mean, it's definitely more than that. Probably 100 would be my guess. That's just a shot in the dark guess, but it's definitely doing more than just 3. And so then that error, I'll do that minus the 1.105167. And I ended up with an error of, ooh, let me write it. Sorry, I ended up with an error of 4.25 times 10 to the negative 6. Okay, so that's like really not that bad, right? It's pretty good. That's, I'd say, a pretty solidly good estimation. Cool. All right, so I did ask for another part. Let me scroll back up so you can see, because there was more to this question, and so I want to make sure I answer it. We answered part A. Find the third order Taylor polynomial. Check. Circled it. We answered part B, which was estimate e to the 0.1. Check, we're good. Now I want to find the Taylor series. So now I just do the same thing, but infinitely many times. Not an integral. You just actually write it as an infinite series. Centered at 0 means this is a Maclaurin series. So recognize a pattern. So what do we think? And I'm going to write that as the Maclaurin series because we're centered at 0. The Maclaurin series for the function e to the x's. Like, let's look at the work we did. If I were to do more derivatives, would anything change? Be exact. Can you see the pattern? Cool. And if I were to do more than just up to cubed, can you see the pattern? Yeah, totally. So it would probably end up looking like 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. I can imagine that going on forever. And then I write that on sigma notation, and it's the sum from n equals 0 to infinity of x to the n over n factorial. Ta-da! We'll talk about an interval of convergence for that power series soon, but that's all there is for that one right now. All right, so now we have this next little bit is all about Taylor's theorem and estimating my error, like getting a better understanding of how off I really am. So if you have a Taylor polynomial, like the one we just did was a third order Taylor polynomial, the remainder in using that polynomial is this guy right here, which is a true genuine equal sign by definition. The remainder is equal to your actual function minus what you used to estimate the function with. That's just your actual error. That's it. We called it a remainder. It's just an error. And then Taylor's theorem is actually quite impressive. The proof behind Taylor's theorem is beyond the scope of this class, so we're not going to talk about the proof of it, but it is kind of fascinating, so I think it's worth our time to understand it. I'm going to label some things on here so you have it. This is the exact minus the estimate equals my error. Cool. Okay, and then Taylor's theorem says not only do I know what my error is in reality, like if I knew the exact, Taylor's theorem says let's estimate that error if I don't know the exact. That's the cool part about it. And so Taylor's theorem says that if you're using the nth order Taylor polynomial, and then the remainder is actually going to be equal to the first neglected term, ish. I really meant the word ish there, because notice the variable changed. It's now plugging in c, where c is some number between x and a, and I don't actually know what it is, because we're talking about if I don't actually know the exact value, we are just going to be estimating it. Okay, and so that's what Taylor's theorem is, and then this next theorem that I have right here is how do I use Taylor's theorem? And that is that next derivative, bound it by some number, we're going to call it m for the maximum value of that first neglected term, and then I will have a bound on the error. And then I'm going to have a bound on that error. The proof behind this we're not going to talk about today. It does use a lot of mean value theorem from Calc 1. If you're interested in looking at that proof in the textbook, it does use a lot of mean value theorem and Rolle's theorem from Calc 1. So it's definitely something within your scope if you're interested, but it's definitely beyond what is required for this. Okay, so let's just do the example. Let's find some Taylor polynomials. Let's just find the first and second. Let me just find the second. Let's just find the second Taylor polynomial for this function at centered at x equals 4. And then use these polynomials to estimate the square root of 6. We're just going to go through and try to estimate what the square root of 6 is. And then we're going to use Taylor's theorem. This is key, the theorem that I just said above, to bound that error. Like, how off am I ever going to be in estimating the square root of 6? Okay, so let's first by just doing the second order Taylor polynomial. So the first thing I do is write out the function, which is the square root of x. And if I want to do the second order Taylor polynomial, I just need 2 derivatives. So I'll just find 2 derivatives. My first derivative is 1/2 x to the negative 1/2. My second derivative is negative 1/4 x to the negative 3/2, and we are going to center this at, where's my center here, at x equals 4. If I plugged in 4, I got 2. If I plugged in 4 here, I got 1/4. If I plugged in 4 here, I got negative 1/32. Now I'm going to add more to this chart before we're done. Taylor's theorem does require the first neglected term to identify the error. So even though I'm only going to go up to the second derivative, I should use the third as well. So I'll do one more derivative, and that gives me a positive 3/8 x to the negative 5/2. It's just worthwhile to have that in front of us. Okay, but either way, let's do the second order Taylor polynomial. So my second order Taylor polynomial is f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared. Okay, and then we are going to use that to estimate the value for the square root of 6. So the square root of 6 is approximately equal to the second order Taylor polynomial at 6, which is 2 plus 1/4 6 minus 4 minus 1/32 over 2 factorial 6 minus 4 squared, which I just typed into my calculator. You could turn all those into fractions if you don't need your calculator. If you don't want to, you can just turn all those into fractions. It'll make it easier. But I'll just write down, I got 2.4375. Cool. So that's the approximate value for the square root of 6. Cool. But let's do the bound on the error. Let's use Taylor's theorem to bound the error. Okay, so I'm going to write down what I need for the estimate of the remainder. It says, Taylor's theorem, if you were to go back to the page before, says that the remainder, and I think it does use a lowercase n, so I'll be consistent, is going to be less than or equal to m times x minus a to the n plus 1 over n plus 1 factorial, where m is the maximum value of that next derivative, which in this case is the third derivative. Only on the interval between 4 and 6. I don't care about beyond that. My center was 4 and 6 is what I was estimating. Anything beyond that is irrelevant in the context of this question. Okay, so then maybe I should spell that correctly. 4. Okay, then I'm going to do this. My third derivative, we already calculated it above. It was 3/8 x to the negative 5 over 2. You can go ahead and graph that in Desmos. Graph that in Desmos, but only for x in the interval from 4 to 6. Cut it off between only 4 and 6. You're going to see the largest value. The largest value that this function gets between 4 and 6 is 0.01171875. I just got that straight from Desmos. Straight from Desmos. I just plugged that in and I got the maximum value. So there we go. There's my m. So that means this is your m. Then you have everything that you need. So that means that the bound on my remainder is going to be less than or equal to 0.01171875 times x minus a cubed because this is n plus 1, so one higher than the second order Taylor polynomial that I just did, over 3 factorial, where x was 6, that's what I was estimating, and a was still the center, so a was 4. And then you can type that into your calculator. Let's do that. So I got 0.011711875 times, okay, and I got 0.015625. So I don't know right now, truly, what the square root of 6 is. I estimated it right here. I don't know what the true value of the square root of 6 is, but I do know that if I use that second order Taylor polynomial, whatever my error is, I don't know what it is smaller than 0.015625. I don't know what my error is, but I know it's smaller than this. So in your calculator, for example, they probably didn't stop at 2. Let's say they went up to 100. Then they would do this same thing, but for 101, right? And then that's how, whatever that number here is how small your error is. You can imagine if I were 101 factorial on the bottom, this number would be a lot smaller. So the more terms you do, the better your estimate is going to be. Ta-da. All right, let's do a little bit more. Let's do a little bit more. So this next one, there's not a whole lot to talk about for this one, but I want to at least visualize it for you guys. How do I know my Taylor series is any good? This is what this whole page here is going to be about. So this is the convergence of Taylor series. If f has derivatives of all orders, I can just keep taking derivatives. Then if the remainder goes to 0, then, let me say that again. If your error approaches 0, that error that I just did right before this, if that error goes to 0, then your Taylor series converges to the actual function in question. So not only does that infinite polynomial look pretty close to sine of x, it actually is sine of x if I were to let that approach infinity. So not only does it look just like it, it's actually equivalent to if I could go off to infinity. So its limit approaches. So it converges to its function that it's representing. Okay, so all you have to do for these kinds of things is to figure out, we just need to show that my remainder approaches 0. So I just want to show that if my error approaches 0, then it's a good Taylor series. So let's write this down. This is what I want to do. I want to show the Maclaurin series for sine of x converges to sine of x for x in the interval from negative infinity to infinity. So what it is I want to show that the limit as n goes to infinity of my remainder goes to 0. That's what I want to show. But I also know what my remainder is. Remember, it was the n plus first derivative at some point c that I don't actually know what that c value is, times x to the n plus 1. That was by Taylor's theorem above. And we know, this is kind of key right here, we know that no matter how many derivatives I take of sine, it's going to be either cosine, sine, negative cosine, or negative sine. Think about the derivatives of sine. Is it ever going to be anything that's not sine or cosine? No, it's always going to be that. We know that this is going to be, is equal to plus or minus sine or plus or minus cosine. And what do we know about sine and cosine? Yeah, we know that it's always less than or equal to 1. So we know that the remainder in magnitude is less than or equal to this whole thing right here. Let me highlight it. This whole thing, it's going to be either sine or cosine. So it's less than or equal to 1. So that means it's going to be just the x to the n plus 1 over n plus 1 factorial, and then just throw in a limit, and then we're done. Let's take the limit as n approaches infinity of Rn of x, which I know what Rn is now. It's x to the n plus 1 over n plus 1 factorial. As n goes to infinity, you get a number over a really large number. It goes to 0. Ta-da. So therefore, This Taylor series for sine of x does converge to sine of x. It converges to sine of x. So let's write this down. I have a conclusion here. This one's not always easy. This is where it's going to get a little bit more challenging, but it's going to be worth our time to practice. So my conclusion is that sine of x actually is equal to its Taylor series. Now you might want to pause the video right now and go back a couple of pages and find the Taylor series that we found for sine of x. We did this one earlier in this video, so I'm just copying it down. But now I know that not only is it a really good approximation, it actually equals sine of x. The only thing I haven't found yet, and this is where it's about to be, this is the key. This is the key. I know this is a heavy section. This is the key right here. We need to find the interval of convergence. We know that it converges, but I want to know when. Is it going to converge for every single x value? I think so, but I don't know. Remember how the geometric only converged between 1 and -1, so I have no idea really right now. I feel like I should figure that out. I want to figure out the interval of convergence. So I'm going to tell you right now how to find the interval of convergence. And this is always the best idea. All right, so always going to be, I'll keep this the same color. To find the interval of convergence, your life will always be easier if you start right away with the ratio test. We're just going to find the interval of convergence, and we did this earlier in chapter 6, so I know you've seen it before. We just now need to do it again. Let's do the ratio test. The ratio test is the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, which is the limit as n goes to infinity. There is an absolute value, so I get to, from here on out for the rest of this particular problem, ignore the negative, because I got an absolute value, so the negative is gone. Everywhere else, I need to just plug in an n plus 1. We can do that. That's going to become x to the power of 2n plus 1 over 2n plus 1 factorial divided by the original is the same thing as multiplying by the reciprocal. And when I say original, I mean this original up here without the negative. So dividing by that original, I just multiplied by the reciprocal. Now we do the algebra. This is the limit as n goes to infinity of x to the 2n plus 3. I distributed the 2 and then added the 1. And then on the bottom, I have a 2n plus 3 factorial. Same thing. I distributed the 2. And then added the 1, okay, and then times a 2n plus 1 factorial over x to the 2n plus 1, and then I simplify algebraically. There are some things that are going to simplify. You can subtract those exponents right there, and I'm going to end up with an x to the power of 2 when I do 1 over the other. I subtracted those. So far, so good. Yep. Okay. We got it. Okay. And then over 2n plus 3 times 2n plus 2 times, remember factorial, you just keep going down 1. And then I'm going to stop at the 2n plus 1 so that it can cancel with what I have on top. So then that guy is going to be canceled. And then this will end up with the limit as n approaches infinity of x squared over 2n plus 3, 2n plus 1. Take the limit as n goes to infinity. X is just a number. You're taking the limit as n approaches infinity. So a number divided by a really large number. I got 0 for all x. Okay, the last thing here, this is the huge conclusion. So far, we have discovered that sine of x has a Maclaurin series, because we did this whole thing centered at 0. Centered at 0, the sum from n equals 1 to infinity of -1 to the n, x to the power of 2n plus 1 over 2n plus 1 factorial. Not only does that equal sign work, that equal sign is true. We proved that with Taylor's theorem. We also know that it has an interval of convergence, and it converged for all x. So sine of x is a fantastic Maclaurin series because it converges for all x. So going back to that Taylor series, I started off with getting slightly better, slightly better. If I were to do that forever, like literally forever, they are in fact equal. So sine of x is just an infinite polynomial. We could have done that exact same thing for cosine, for e to the x, all kinds of functions. So now we have this idea of functions turning into infinite polynomials. That's the big picture for our Taylor series. All right, that's it for now. I'll see you guys next time.